Welcome to Chapter 11, Section 3 now. We're going to be talking about the properties of waves. And we are going to look at this first part here where we're just talking about what mechanical waves are. So what we're going to talk about is we are going to distinguish local particle vibration from overall wave motion. We're going to differentiate between a pulse wave and periodic waves. And we're going to relate energy and amplitude. So when we talk about wave motion, your textbook describes it as the motion of a disturbance, like dropping a rock in a pond. So anytime you drop water in something, right, you get this ripply effect. Okay, that is what we call wave motion. Almost all waves need a medium to travel through. But what is a medium? Well, a medium is the substance through which a wave travels. So for example, if you drop a rock in a pond, right, you get these waves in the water. So the water is the medium that the wave travels through. It's whatever is actually waving as it goes through. So mechanical waves now are waves that require a medium to travel through, like air or water. And electromagnetic waves do not require a medium. So examples of mechanical waves are like anytime water waves, like you drop something in water and you cause waves, or there's the waves in the ocean. And air, sound is a wave that travels in air. Air is the medium for sound. Electromagnetic waves are a kind of waves that do not require a medium. So examples of electromagnetic waves, light is the most obvious one, but radio waves, microwaves, X-rays, those are all kinds of waves that do not require a medium to travel through. So for now, we're only going to discuss mechanical waves, so you can kind of just forget this for the moment, although you should know that they exist. And we will talk about electromagnetic waves in another video. So there are two types of mechanical waves that we are going to talk about. We're going to talk about pulse waves and periodic waves. So a pulse wave, this is a type of wave that is just one wave that travels through a medium and does not repeat. So you can imagine if you had a little man standing here, right, and somebody's holding onto a rope, okay? If they lift the rope and send it back down, they're going to create a wave that travels along the rope. As long as he only does that once, you'll get this one wave that travels, and that is a pulse wave. So anything that happens just once is a pulse. Periodic waves, on the other hand, this type of wave comes from repeated motion, okay? And once the source of a periodic wave stops, the periodic wave ends and you have the last pulse wave, okay? So you could talk about each wave, each here, this is one pulse and this is one pulse, but all this whole thing together is a periodic wave because it repeats. So really the key part here, right, like with periodic motion, it has to do with this repeating. So repeated motion gives you periodic motion, and a repeated pulse wave gives you a periodic wave. So when we look at mechanical waves, we need to think a little bit here about what is moving. So what we have here is when we look at a wave on a string, okay, what part of it is moving? Okay, so imagine that this is a rope, okay, and you've got a particle of rope, and that single particle will just move back and forth. So if I chose this point on the wave, this point on the wave is going to travel all the way up to here, and then it's going to travel all the way back down. This part of the wave, right, it travels up and it travels down. This part of the wave, right, it travels down and then it will travel back up. But the rope doesn't actually move forward. This particle doesn't suddenly end up over here somewhere, okay? Because you could imagine you're holding on to the end of the rope, right? It doesn't go anywhere. So these particles just go back and forth. So this particle experiences simple harmonic motion, and so does this one, and so does this one, and so does every single particle on the rope. But what we say is the rope as a whole, the whole thing here, it has wave motion. Okay, so make sure you can understand that difference. A particle goes through simple harmonic motion, but the whole thing together has wave motion. And this is true for all types of waves. It's easy to think when you see an ocean wave like this that the water must be moving, okay? Now, particles in a water wave, they don't specifically travel up and down, okay? They actually travel in little circles. But still, this particle of water doesn't suddenly end up over here somewhere, okay? It just travels in this circular path. So this is periodic motion, and we can even sometimes pretend that it's simple harmonic motion. But either way, the particle does not move, and that's really key, okay? The particles don't travel. Okay? The particles do not travel. So then that kind of begs the question, then, what is actually moving? The particles just go up and down, so what seems to move? Well, the trick here is that waves carry energy, not matter. So anytime a wave travels, and you can see the wave, right? It starts here, and then it goes here, and here, and here, and here. And you can imagine a new wave starts, right? And it's going to come down and move that direction like ocean waves do. So what actually moves? Well, what happens is that is carrying energy, okay? The matter moves up and down, but energy is carried forward. And this is true of all waves. So let's look at another example of this, okay? You could think about ocean waves. They're the most obvious one, okay? So the waves, they carry energy, okay? So these little waves, like this little dog, I thought he was really cute, riding a surfboard here, okay? He is on a small wave. And you could imagine if you were standing in front of that wave, right? And that wave hits you, it might make you move a little bit, but it's not going to do much to you, right? But if, on the other hand, you look at this surfer, right? He has just fallen off of his board, and this is a huge wave compared to that one, right? It's a lot bigger. If this wave hits you, that is going to hurt. That is going to be painful, okay? And the difference is you have this energy causing a force, okay? So these waves carry energy. And the bigger the amplitude of the wave, the more energy the wave carries. So this wave has more energy than this wave, which has less energy. Now, if we look at this, it turns out that it's a proportional relationship. So the energy carried by a wave is proportional to the square of the amplitude. And the way that we can write that is we're going to use an E for energy, like we always have. And we haven't used this before, but for proportional, we can use this symbol here. Okay, that means proportional to. And it's the square of the amplitude. So we'd say the energy is proportional to the amplitude squared. What that means then, let's look at an example. Okay, if we take this wave, and if this wave is one height, okay, or that would be its amplitude, let's use that letter instead, then this wave's height, if they is double, which is probably a lot more, but if this one's A and this one is 2A, the energy will be squared. It will increase by a factor of 4, okay? So you would have energy here, and this would be 4 times that amount of energy, even though we just doubled the amplitude. Okay. So that is the end of our introduction to mechanical waves. Please let me know if you have any questions in class, and I'll see you there.